Okay, hello everyone. I'll be going over the problems now. So for the first problem, basically we have something that looks like this. They're just two gliders that are connected, A and B here. Wait, no, that's A prime, actually. And then there is another one here in the middle, B, that can only move in between these two other gliders, and all three of them can move along the floor, which is frictionless. And so here, the distance that B can move between is 2L, and the mass of yeah this they have the masses M, and here let's see. Yeah, the glider B has mass small m, and the glider A and A prime, they have a combined mass of big M. And so at some point the system is at rest, but then there's some cap between A and B is exploded, and this gives a total kinetic energy T to the system. And so we want to find the period of B's motion in terms of T, L, M, and M. So let's say that this glider B here, this goes with a velocity of V M small m, and then the big glider goes in the opposite direction with a velocity of V big M. So now we can set up some equations. First, the really obvious one is M times Vm is equal to big M times Vm from conservation of momentum, because the total momentum is 0. And then we also have, from conservation of energy, the kinetic energy here, it would be 1/2 m Vm squared plus 1/2 big M times V big M squared, and this is equal to the kinetic energy, which is T. That's given from the problem. Okay, so now now we can just solve these two. We have 1/2 times m Vm squared plus m since V of big M is equal to m over m Vm, then we would have this is plus m times over big M V squared. And this is of course equal to 1/2 times 1/2 times m times 1 plus m over m, and all of this multiplied by Vm squared. Wait, yeah, and this is equal to 2. Okay, so now we can solve for this. Vm would just be equal to, then it would just be equal to square root of 2Tm over m times small m plus big M, I believe. So that is V of small m. And then obviously this means that V big M is just equal to this times small m over big M, and that's equal to 2T times m small m over big M times m plus m. Okay, so now we have our two velocities. And so if we look at it from the frame of the big glider, that the A and A prime, in that frame, the big glider isn't moving, while the small glider B would be moving with a velocity of Vm plus the V big M. So then in that case, one period, since it takes, since the one period would be back and forth across this length 2L, so that would be 4L. So then since in this frame, the big glider doesn't move, it's just basically this small glider going back and forth at a constant velocity at a constant speed, since the floor is frictionless and all the collisions are elastic. So then the period would just be this total length, which is 4L over Vm plus Vm. And then we can just plug in our two values. And then this would be 4L times over 2T m plus. And this is equal to 2L times square root 2 over T times m plus m. And so that is our final answer. Does anyone have any questions? Okay, then I'll move on to the second problem. So here in the second problem, we have a piston with a spring in it, pushing on its head, and the spring has a spring constant K. So it would be like this. And so there's some gas inserted into the piston from the left, and the pressure from this gas compresses the spring a distance of x. And yeah, and we know that the gas is held at constant temperature by contact with the environment. And so here now we want to find the x such that neither movement to the right nor movement to the left is spontaneous, meaning that it would lead to higher total entropy. And this is basically just the equilibrium position of the piston. So we want to find this x. Okay, so the entropy is the ds is equal to d w over t for the work. Wait, no. In this case, it would be the same. It's actually dq over t, but in this case, it's the same as dw over t. Oh wait, or there's no d actually. I believe it would just be w over t. Yeah, dq is just equal to w in this case, and this w is the work, and we know that since the dw is equal to p dv, this would be the integral of p dv from v1 to v2. And so this is, of course, equal to integral from v1 to v2 of nRT dv over v, since from the ideal gas law, PV is equal to nRT. And this is equal to nRT times log of v2 over v1. And so then, of course, the entropy ds would just be equal to nr times log v2 over v1. Okay, so now if we move the piston to the left a bit, so that if we move the piston to the right a bit, so that x increases, then we would have the volume of the gas would increase to, say, will increase by, say, dv. Okay, so then here, then so then in this equation, it would be equal to nr times log of v1 plus dv over v. There's no need for this v1 actually. Here, so it would just be log nr times log v plus dv over v, where v is the original volume here. So this is of course equal to nr times log 1 plus dv over v, and since dv is over v is really small, we can approximate log of 1 plus x as just equal to x if x is much smaller than 1. So then this would just be equal to around nr over v dv. So this is what happens if the piston moves to the left of it. This ds would be the entropy of the gas. Now, if the piston moves slightly to the, if the piston moves, yeah. Okay, so if the piston moves little to the, wait. Yeah, this case would be with the piston increasing. Okay, so now if the piston moves to the right, we just analyze what happens to the entropy of the gas, because as before we found the entropy of the gas is just equal to d q over t, and so we ended up with this answer. But the surrounding of this, the surroundings of all this system, it also has an entropy. And so now if we look at that, since the energy of the gas stays constant, this is because the temperature is constant. So that means that heat must enter the gas from the environment. And so then this just means that the entropy of the environment goes down because some heat is lost. And this would be, again, since it's just dq over t here. Okay, so now, since now we found the end of the entropy, what happens to entropy of both the gas and the surroundings if the piston moves to the right. And since now we analyze the situation where the entropy doesn't increase. Yeah, so since we know that the entropy doesn't increase when the piston moves to either the left or the right, we just need to analyze the right side and make sure that it's when we find the x where it's 0. So since the entropy of this, the surroundings goes down by dq over t, and that of the gas goes up by this nrv dv, then for them to add up to 0, we can just set them equal, and so nr over v dv is equal to dq over t. Okay, so now we want to find the x here. Okay, so now we know that this dq here is just equal to the work. And so what is the work? Well, it's just the force times the distance. The force from, and here it's the force from the spring, which is of course kx, and then times the distance, which is just dx. So then this would be kx dx over t. Okay, so now for our next step, we can write that since dv is just equal to a dx, a is the cross-section area, and a is just the cross-section area, but a is also equal to v over x, in fact, which you can quite clearly see. So this is equal to v over x dx, which means that dx is just equal to x dv over v. So then we can just plug this back in. So then we can just plug this back in. nr over v times dv is equal to it's equal to kx squared dv over vt. And now see, so now we can easily solve for x. We can cancel out this v and the dv, and this would give us x is just equal to square root of nRT over k. So that is the answer to the second problem. Does anyone have any questions? Okay, then, since no one has any questions, then that's it. And thank you for listening.